A7.
A7, eh?
Splish!
B1.
You sunk my battleship. Being stupid. This ship sank anyways.
No, I never really thought about that. Do this.
I don't know.
Let's go find out. Couldn't find a single one on my ship sink or float.
I couldn't find anything.
That's ridiculous.
I know.
This just in, local man Archimedes determines why things float and sink.
Eureka! I've discovered why things float and sink.
For our experiment today, we're going to be using these water bottles filled with salt of different weights to try to prove Archimedes' principle.
Archimedes once said, "Any floating object displaces its own weight of fluid."
In this first trial, we're going to measure the water displaced from this bottle. 50 grams of salt should displace 50 grams of water. To find the relationship between displacement and mass, we did a second trial with 100 grams of salt. Our third and final trial to prove this linear relationship, we used 150 grams of salt, and we're going to displace 150 grams of water.
Buoyancy is determined by the density of the object as well as the density of the fluid.
We crushed the 150 gram salt bottle to lower the volume of the bottle, therefore increasing the density. Because of this increased density, the buoyancy force was totally overcome by gravity, so the water displaced ended up being less than the mass of the bottle. Because we changed the density and the bottle sank, the linear relationship was not held.
At a constant volume, heavier objects sink faster.
So in this experiment, we're going to add slight amounts of salt to try to increase the rate of sinking on this little bottle here. So in our first trial, we put it just above the surface of the water and let go. You can see that it comes up at a slow rate. But as we add more salt, we're going to see the acceleration or the force of gravity acting on top of the buoyancy force, overcoming it and causing it to sink faster.
In this set of experiments, all of our salt bottles have enough density to sink to the bottom of the glass. Buoyancy force is entirely dependent on the density of the water and volume of the bottle. And since each bottle fully sinks, the buoyancy force is equal in each trial, no matter the mass. Therefore, heavier bottles will sink faster than lighter bottles.
So, as the object goes into the fluid, it has to make room for itself by pushing the fluid out of the way. Since the fluid has nowhere else to go, it has to go up against the force of gravity. This continues until the force of the object pushing down on the fluid is equal to the force of the fluid pushing up on the object.
Giant ships are able to stay afloat due to the design of the ship. The 150-gram bottle was able to float when its design was uncrushed and had a greater volume. Similarly, the hull of a ship utilizes a large volume, which will create a massive upward buoyancy force, which is able to overcome the weight of the rest of the ship. For example, the German battleship Bismarck weighs 41,700 tons, which is equivalent to 6 Eiffel Towers, and even though 40% of its weight comes from its armor, the hull is large enough to displace the weight of the ship and keep it afloat. However, whenever a ship's hull is breached, it will fill with water, increasing its weight, thus causing it to sink.
Man, I'm really glad we learned about buoyancy.
Yeah, just think of all the stuff we could use it for.
Yeah, it's so exciting. Let's finish this game though.
Okay, H8.